So maybe let me briefly recap some of these ideas again, and then we will revisit. Okay? That could be beneficial. Uh, the first is so if you want to understand, you can have a representation of types. So let's say the basic type could be like, this one here, so I have a very interesting problem now. So in my office, I keep in class, I keep my office, I keep my writing pad in certain angles, so my brain is all trained to write that way. So now at home, when I keep the writing pad in a different angle and everything is moving in a different direction. But I forgot how I keep my writing pad in office, what angle I keep it. Anyway, that's a different point. So let's look at the basic stuff. Okay, so these are the basic data types if you see. So this is you have an integer, or let's look at integer. Okay? Or maybe I should start from here. So let's say there's a basic type T. Okay, T can be, like for example, it can be int, char, float, double, whatever you have, it doesn't matter. This is the basic data type. And then on the top of it, so you can have another data type, which is pointer to T, pointer to T. Pointer to, so if a variable is of type pointer to T, pointer to an integer, then it contains the address of a memory or the address of an object, and that object holds of data of a particular type. So for example, if it is, we can say something like T star, where T can be any of these things, var, then that means, let me var pointer, so let's say var pointer. Then, so var pointer contains an address of an object, and the type of that object is T. The type of that object is T. Just want to see if I'm able to check the chat. Is it possible to boost my mic? Just give me 1 minute. How is it? Can you hear me better? Can you hear me better or no? Is it the same? You cannot hear me at all, or you can, of course, you can still. Okay.
So we can hear you a bit, but it's very muffled.
Okay. So let me get some help. Okay, 1 minute. Hello. Is it fine or I don't know what to do?
Yeah, so much
So,
better, much better.
okay. Great, great. Then. Okay. So, uh, I'm using a fancy microphone and I don't know how to use it. It's the summary. Okay. So, yeah. So, are you with me here on this, the T star var pointer? T can be in char or in your and then you can go further and then you can say, uh, let me use this word. So, yeah. So, PTR, PTR, T. So, this is pointer to pointer to var PTR, right? So, uh, and then we can keep, no, we can have as many stars as you want. You can have a pointer to a pointer, and just by looking at the address, you don't know whether it is a pointer or a pointer to pointer. So as a part of program logic, you need to have this mental map, the type, what are the different variables and what are their types. We need to have them in our mind. And the declarations that we use in the program, they act as documentation. They tell us this is what you intend to do. This is what the purpose of this particular variable is. So if we, this is, let me use a different word here. Uh, so PPTR, pointer to pointer. In terms of memory, if you draw the memory, if this is your memory, let's say var, this is var, and this address of variable is 100. And so now if you have var pointer, let me use a different color. So this is our var pointer. It contains, it's a pointer. It contains an address of a object, and that object is of type integer. So let's say if this is pointing to this particular integer, let's assume this is whatever, let it be of type p, then this is 100. And if you go one step, pptr, let's say this, the address of this is 200, then it contains 200, and this address is 300. So is this picture clear? So one question Pramod have is, if we have a pointer to a pointer to a pointing to an integer, if you increment the first pointer by 1, it would actually increment by. So Pramod, maybe let's take that question. We'll wait on that question. It's we have to check on it, and so let's get the basics right. So I hope this picture is clear. I hope this picture is clear. So when we access PPTR, what we get is 200. And when we access star PPTR, what we get is 100. Okay, so when we do star, so you, whatever the address that is present in that location, you go there and you read it. right? So an application of star will take us to this memory location and we will read it. And then what we do next is no, star star PPTR. So this will take us to this star star PPTR is whatever the value that is present here. So let's say the value that is present here is some value -1, and that's what we get here. Right? So PPTR is 200. Star PPTR is no, you go an alternate way of looking at it is, you know, when in one of the classes we studied about expression trees, this is also an expression. So star, this is unary expression, star star PPTR. So what is the value of PPTR? The value of PPTR is 200. This is the value of the leaf. And when we apply star on this value, that is, you go to this address and read it. So the value of this node is 100. And when we apply star on this 100, so you get -1. So this is an expression tree. The base of the expression tree, it contains, it's the leaf that is PPTR. Its value is 200. Are you with me on the expression tree? So this expression tree is a nice way to understand what is going on. So this is our expression tree. So now, so if we want to manipulate, if you want to change the content of var, you need to know the address of var. If you want to change the content of var PTR, you need to change the, you need to know the address of var PTR. Like for example, you cannot change the content of var PTR by just knowing the contents of var PTR. You need to know the address of var PTR, and the address of var PTR is present in PPTR.
Oh, okay. So yeah, I think I got it with that. Yeah.
And so let's see. So now let's say you want to write a swap function to swap two variables of type t. Okay, so you want to swap to write a swap function to swap two variables of type t. So if you want to swap two variables of type t, that is, let's say there is var and var a. Let me So what do we have? So let's say this is the memory, and in the memory, so there are two variables. One is var a, other is var b. You want to swap their contents. If you want to write a swap routine to swap the contents of two variables, so they are of type t. Then you cannot pass the values that are present in var a and var b to swap and expect them to be changed. Instead, you need to pass pointers to them. So you need to say ptra. Let me write it this way: t star ptra and t star ptrb. This is what we would like to do. And then what do we do? So here in this program, so we say temp is equal to star ptra, that is the contents of ptr of the variable a. they are assigned to temp, and then we say star ptr a is equal to star ptr b, and then we say star ptr b is equal to temp. This is what we do, right? And if you think about t, this t can itself be int star. Let's say you want to swap two var pointers, 2 pointers, okay? Then the type of t will be, what will be the type of t if you want to swap to integer pointers? So now the story is, let's say, the story is like this. So in this case, t is an integer. The simplest case is t is an integer. But let's say you want to swap two variables, but this is var ptra and this is var ptr b. This is what you want to swap. So if you want to swap var ptra and var ptr b, so this is of type t star. It points to some object which holds which is of type t. This is also of type t star. So if you want to swap, them, if you want to swap these two contents, if you want to swap these two contents, uh, so we need to pass a pointer to var ptra and pass a pointer to var ptr. And so if, and the pointer to var ptra, like the function, in other words, this t all the time remains the same. This t in this particular case is int star. Okay, let's say is of type this is of int star, this is of type int star. So you need to pass a pointer. So in put it in other words, you want to pass the address of this. So the thing that you want to work with is, is this particular data type, pointer to pointer. Does this make sense? Because if you don't know the address of var ptra and var ptrb, you cannot change their contents. So you need to know the address of var ptra and var ptrb so that it is possible for us to exchange the contents. An alternate picture is let's say you have an integer. This is an integer. I'm using a big thing for an integer. Hey, sorry, there's network problem. I'm back. Hey, can you hear me? I'm sorry, my net got disconnected. So sorry. Uh, yeah, I think I hope you got the picture, but I just want to draw one picture for the sake of completeness. So let's say this is a object, a memory object, and this is where the actual data is present, and this is the metadata. And in this metadata, like for example, we store a couple of things. So So let's say this is an integer. So let's say it is of type T. T can be integer or anything. And yeah, so let's see how this picture emerges. Let's say for the sake of simplicity, let's say 100 is present here. And yeah, and let's say you have another data. I'm just thinking, there is one field I used it before. I forgot what that field is. But let's say you have a pointer to type T, and yeah, this is the address, the actual address. So let's say 100 is the address, and the content is let's say -1. This is the address of the object, address of this. So here, let's say the address of this particular object itself is 200, and it's a pointer to uh, to an object of type T. Let's say if this is pointing to this, let's say if this is pointing to this, then this will contain 100 here. This 200 is not the content. This is the 200 is the address. Okay, 200 is the address. Let me use capital A to indicate this is the address. And then again, if you go further here, you can have something like so pointer to of type T, and then the address of this could be 300. And let's say if this is pointing to this, no, then this will contain 200. This will contain 200. So if let's say if the name of the variable is X, so I'll have few questions for you. So that will, if you kind of answer those questions to me, then we will have some idea. Here is the chat box. I'm not able to see the chat box.
I guess you can just speak then.
Okay, so yeah, that's also fine anyway. But it would be nice to see the chat box. But anyway, so this is all. Yeah, maybe it is here. Ah, hiding somewhere here. Yeah, surprising. Why is it all becoming anyway? So so what I am trying to see here is why is the okay. So what? So the few questions for you is what is X? If I say X, if I use X, if I say X is the variable. So if I X, what will be the value that will be returned? The value that will be returned. So is uh, so let's try to do different experiments. So if you use somewhere on the RHS, if you use X, then the value of X, but that will be 200, will be read. 200 is the value that is present at that memory location. And let's say when we use X is equal to, let's say write some whatever 2000, then what happens is you go and change the memory associated with the variable x. This will change the memory associated with variable x. And what is address of x? Address of x is 300, right? And then what is star x? So star x is you go to the, so star x is an alias. Star x is an alias for, so star x is an alias for the address 200. Star x is an alias for the address 200. Okay. So then that means if you use star x somewhere on the RHS, you read the contents of that memory location 200, that will be 100. And if you say star x is equal to something, then the address memory location associated with 200 will be updated. So similarly, if you see star star x is a alias for it's an alias for the address memory location 100, and so let's say if the name of this variable is x1 and the name of this variable is x2, so x1 is an alias for the address 200 and star x is an alias for this. So similarly, so x2, uh, yeah, it is for x2, and also star x1 is a alias for this. So when we use the memory address 100, x2, star x1, star x, these are all aliases of each other. So these are all aliases of each other. So when you use, so star x is equal to something, then what happens is this location gets updated. Okay, so when we do make some change, then this location -1, whatever that is there, it gets modified. So similarly, when we say x2 is equal to something, both these statements are equal. Or star x1 is equal to something, so again the effect will be the same. So this idea that this particular memory location 100, there are multiple ways of accessing it. That is, one is directly x2 or by using a pointer to it star x1. So this is the most direct way. This is star x1 is one level of dereference. The star x is two levels of dereference. All these things are equivalent to each other. So if this basic idea is there in your mind, then when you are writing swap functions, etc., it will become easy for you to work with. All right. So are you with me here? Does it make sense? Okay. So now, so what's next? So what questions you have? With this as the baseline, do you think you can go back to the program and see whether it makes sense or not? Okay. Any questions then? They're all good. Anything you would like me to discuss apart from this? Okay, so if these for basics are right, then I can take any other questions that are there. I don't mind. Pramod has some questions, and any other questions, any arbitrary things we can talk if these basic ideas are clear to you. Pramod, go ahead.
So let's say we initialized a character and a pointer to a character,
Okay.
and then in the next line we initialize a pointer to an integer,
Mhm.
and then if we in the next line if we increment the pointer to the character by 4, then the pointer now points to the the pointer now points to the other memory location, right? The same as the integer one.
Can we try to write it down and see what it is?
Yeah,
Or can you type it in and see how approximately what you have in mind
yeah.
is?
I'll type down the code. So
Yeah. So if you type it on the chat box, then I'll
yes.
take it up from there. See, and I keep looking at the chat box and see all the emoticons, etc. you use. So when as I teach, I keep wondering what does it mean. it's it's a good learning experience for me, and but still, okay, okay. So car ch. Yeah. So what do you think? What's the problem here? Car ch car star ampersand b. Okay, t is equal to t plus 5.
So after the end of this, the both t and the other pointer ptr, both of them would point to the same memory location, right?
No, how do you? We don't know. It may or may not.
Oh, so if we oh so so do they not get allocated like consecutive memory blocks on the stack?
May or may not. We cannot say. So we also don't know whether CH comes before B or B comes before CH just because they are declared one after another. And also the other thing is, no, the stack grows in the opposite direction. So there are a bunch of other things which based on which, but let's say it is quite possible that it points to the address of B.
So why does it not give me a warning? Like
See, no, this is what happens is, I think one thing all of you should understand, and you will get to know with bit of experience, is C is designed to be a programming language for systems programmers. When you write device drivers, when you write operating system kernel routines, when you do many other low level stuff, you kind of play with these things left and right to get your job done. So the compiler, for not sure, does not know for sure what you are doing is wrong. It assumes that you know what you are doing,
yes, makes sense.
right? Because especially you will see the more systems stuff that you do lots of hacks and no, and
एक बेटा नोटिस
so
भी काटते हैं वो हिसाब है फिर को रोक मार देते हैं हंड्रेड और फिर को
someone is talking. Can you mute yourselves, please? So, Pramod, your question is, as I said, two things. We don't know for sure whether they are the same or not. It could be the same, it may not be the same, and all those things. But you have a point. But the thing is, the warnings, etc. C doesn't give because it assumes what you are. The compiler doesn't give any warning to you. It says you better know what you are doing.
Yes, sir.
Okay, so See, how do we know that other thing is whether memory for CH will be allocated before B, or it depends on how the variable C, when compiler processes these variables, it could store them in a symbol table, and when it is laying out memory for them on the stack, the symbol table, no, it could be storing the variables in a sorted order or in a reverse sorted order or whatever it is. So depending upon all those considerations, the relationship between the memory address for CH and B changes. And the other thing is you are kind of forgot char star T, no? That T is also a local variable. So it is also allocated memory on the stack. Then why is it that the T doesn't come in between the memory for CH and B?
Oh, oh yeah.
Hmm?
Yeah, true. Yeah.
Yeah, so
So initially I thought it should be t is equal to t plus 4, but when
hmm.
I ran the code, it gave me like 1 byte short. So I did t plus.
Uh-huh.
I have no idea why it's 5.
Okay. So yeah, there are multiple reasons. There are other reasons also. Like what happens is in order to make the systems run fast, uh, sometimes no, the addresses you want them to be word aligned or no, or the address should be a multiple of 8 bytes or multiple of 6, multiple of not 8 bytes, multiple of 8 or multiple of 16. So in order to get that nice address, which is a multiple of 16 or 4, you may end up leaving holes in the memory. That is, no, that memory will not be allocated for any purpose.
So in C programming, is all of the memory available for us to read and write? Like, does it not complain about anything? I
What do
mean,
you
all
mean
of the
by
memory
all
in
of the
the
memory?
like in the stack and heap. In heap exactly, actually.
Uh,
Like, are we allowed to access any byte of memory?
See, there are restrictions. There are restrictions in the sense, no, like for example, oh, I got an orange color. Yes, I am back. So theoretically speaking, it is quite possible that the whole address space should be available, theoretically speaking.
So, what does malloc exactly do on a low level? Does it? So, I first I thought it's changing the permission of some memory block. So, does it only like what does it do exactly?
So good question. So malloc is very simple. It's like let's say malloc has 1 GB of memory to manage. It's a kind of a underlying runtime system. Let me not use more words here, more terminology, but it's a what happens is yeah. So you have let's say 1 GB of memory is available on the heap. So when you ask for, you use an malloc call and say, I need 100 bytes of memory. So malloc looks at that 1 GB of memory and carves out that 100 bytes and gives the base address of it to you. So as you keep making calls to malloc for memory, malloc keeps It looks at its free pool of memory, and if it is able to serve your memory request from the free pool, it will give it. Similarly, when you free memory, then what happens is it adds that memory back to the free pool. So as you do a sequence of no MLOps and frees, your memory kind of gets fragmented, that some patches will be allocated, some patches will not be allocated. But MLOp keeps track of all these things: what is allocated, what is not allocated. And when the next call for MLOp comes, it will look for the free patches and tries them and try to assign them to you. And that's what the job of MLOp is.
But it's only for small requests, right?
No, you can ask for large amount of memory
But
also.
then it doesn't allocate on the heap itself, right?
Oh, is it?
BRK or mmap, like it decides between that, right?
Or is it that I am not sure, but it is, but it may use it to get more memory, but it is still under, it still falls under heap only, right?
Do we call it heap if it's a totally different page?
No, page is for a different thing, but yeah, so I don't, beyond what is said, I'm not exactly sure about how MLOG grabs memory from the operating system, but
So you can do strace and mloc for small amounts and large amounts, and for small amounts you can see it call sbrk, and for large amounts it'll call mmap.
for
So
large amounts, it will come
mmap,
mmap.
yes sir.
That could be an optimizing thing, but what I would say is no, but all of the technically could be, we can uh, yeah, technically we can, logically we can say all of this falls under heap, logically speaking. That's the chunk of memory which is managed by MLOC.
Okay, sir. And another question, sir. You said sometimes it can be aligned to 16-bit boundaries, right?
Yeah, yeah, that's true.
Is that only for SIMD registers or for all registers?
Not only SIMD, like for example, if you are using long double, maybe if you may need 8 bytes, right?
Long, okay, yeah, long double, yeah.
Long double, or in some, and when I was reading C standard, what I understood is, uh, so what I understood is the C standard says a lower bound for the size of the memory. Like for integer, the C standard says you should have at least 4 bytes of memory, but it could possibly go for maybe 8 bytes or 16 bytes also. It looks like that. So whenever, when the address is not aligned, word aligned or 16 byte aligned or 8 byte aligned, depending upon the data that we are accessing, you can get serious performance problems. There will not be correctness problems, there will be performance problems. There could be correctness problems in some processor architectures, but we don't need to worry about it. But there will be, for Intel processors, there will be performance problems.
It won't even load, like with SIMD. If you try to do unaligned, it gives a general protection fault, like it'll just error.
Oh, is it? Okay.
Yeah.
So even without SIMD also, Kishore, like even for, even if you don't use SIMD also, there could be issues in if it's not properly, addresses are not aligned.
But everything else will automatically get corrected, right? It'll.
Yeah, that's true. It will all be done automatically. That's true. Yeah. What is Karthik saying? I still don't get it. What you don't get it? I don't get your emotion or emoticon. So what is it? You tell me that and I'll help you out. Let me understand your emotion or emoticon.
Sir, no, I was like he was talking about SIMD and
Oh, SIMD. Yeah. Okay. So
I didn't know what it was.
don't worry about it. So whatever no Kishore asks, I also don't know most of the time. So
So no, I googled it and I kind of got it.
okay, good, good. So yeah.
Wait, I'll give. What?
Okay. So yeah. What else? Yes. What
Sir, one
else?
doubt.
Yeah.
So after many malloc calls and frees, the memory will be fragmented, right?
Yeah,
So
that's true.
if we uh, so now let's say we ask the malloc to give us a large chunk of memory,
Hmm.
and that size of memory block is not available, like a contiguous size
Ah,
not
okay.
available. Is the malloc allowed to like pause for a moment and rearrange blocks? But that
Mm.
would change the addresses of.
Yeah, that's true. It already gave the addresses to the user, right? It cannot
Yeah.
change it.
So
So
what does it do?
I think it will just give a uh, null pointer saying I will not be able to serve your request.
Oh, okay.
Yeah, so it's a good question. Um,
What was the question?
yeah,
Oh,
the
so
question is yeah, go ahead, Pramod, explain.
yeah, so the question was, after many malloc and free calls, the memory is like very fragmented now. And if we ask the malloc to give us a large chunk of memory and that size of memory is not available, like a contiguous block, then what does malloc do? Like, is it allowed to pause and then rearrange some memory? Because if it does that, then then many addresses change, so it's not allowed to.
Yeah, but then when we wrote that program to crash your PC, then malloc, I mean, malloc uh, is converted to mmap, so it's the same thing, right? And then it didn't return null; it just crashed the PC, right? Or
Uh, what is it, Kishore?
so remember when we wrote that program to crash the
Ah,
crasher?
that's true. Yeah.
But then malloc didn't. I mean, mmap the same thing, so it didn't return null, right? It just crashed the PC.
I don't think so. MLOC, when it becomes full, if it doesn't work, it returns a null pointer.
But why didn't the mmap calls then also?
Maybe are you checking the return value or see it could be crashed for a different reason. Uh, there are a couple of reasons. Maybe we are not checking the return value of mmap and still going ahead and doing our stuff. Uh,
Because
that's one.
without the fork, the OS had to kill it.
Without the
Without the fork, the OS killed the
ah,
process.
that's
So, does it return null or does it just
MLOC.
yeah? No,
MLOC,
mmap, but
mmap, we
same
have
thing.
to see how, if you kind of see, let's say, return value of mmap. So my doubt is there are two things. It may crash because of performance reasons, or, mmap void mmap, we can see this. How do we know if something is not tolerate? On success, mmap returns a pointer. On error, yeah. So I think, see, if I think at some point when mmap fails, like we have to go and check this error map underscore fail. We are not checking it.
Okay. Okay, so maybe it was failing, but
Yeah, we are not checking it. That's my guess.
okay.
Sir, I think my doubt was similar to Pramod's. I think I typed it in the chat today in the morning. But yeah, when Rudransh was asking something about data interfering when you're using malloc, right?
Data?
So he talked about data interfering, right? Like
I
if
didn't see
I
the
can ask
chat.
his doubt.
Yeah, please
I
go
remember
ahead.
his doubt. His doubt was basically if you malloced 50 bytes and you casted it to integer pointer,
Okay.
so it's not a multiple of 50, right? So what will it do there? Was the question.
no, 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 that wasn't the question. That was not
Wait,
that question. This
oh,
was
another one.
he
Sorry.
asked it. He asked a different question. So his question was okay. I'll try phrasing it in my own words. Like this was what I wanted to ask you. Like suppose I malloc two different pointers. I give so they'll be given separate memory locations, right? In heap,
Mhm.
not necessarily contiguous.
Okay.
So now if I take the first pointer, let's say it's a character pointer, and I fill it up with like an infinite string that completely like fills heap,
Okay.
then where would the second pointer be pointing? Will it still be pointing to the same place it was pointing to in the beginning?
No, see, you, let's say you got address of two house, and you just kind of wiped out the residents of one home and have someone there. So the address still remains the same, but some other people are there because the address remains the same, right? Let's say one malloc call gave an address 100 and another malloc call gave an address 1000. And you started with the malloc call with the address 100 and you wrote an infinite string. So that means you end up overwriting the memory locations pointed to by 1000.
Yeah, so then if I start writing from the second pointer, it will just overwrite everything, right?
Sorry?
Now after I filled everything, so the second pointer is still pointing to some memory location. That's obviously full. No?
That's true. Because see, all we are saying is this is what I want you to understand. Okay. If you understand this particular idea, then you will. There is what malloc and free gives. These are like two primitives that are given to us. Malloc returns memory and the base address allocates memory. The base address will be given. And so that's all. And this is the, using this, we want to build a castle. Okay. When you later on, when you study data structures, you build very complex data structures. And that data structure, the semantics of the data structure, it is all in your mind. Malloc doesn't have any clue about all those things. And it is your job, like for example, if you are given 50 bytes, but if you end up using 100 bytes, then you don't know what happens, because the next 50 bytes could be allocated to some other object, or you could have overwritten some metadata, and because of that, the whole heap structure, it could have been destroyed. So anything could happen. So, and the 100 bytes of data which malloc gives to you, it doesn't know whether you want to use that 100 bytes to store an array of characters, or you want to store an array of no integers, or you want to store an array of floating point numbers, or you want to store an array of structures, or you want to store one structure whose size is 100 bytes. Nothing of that malloc knows. Does it make sense or not? I mean,
Yeah, so all malloc does is you ask it to allocate memory and it'll allocate memory. That's it.
yeah, and if you don't respect that memory, if you overwrite it, then it is undefined. What happens is undefined. It depends upon, there could be multiple implementations of malloc library, and let's say there is a program that you have written where by accident you kind of made an error, and when you tested your program, it all worked out fine. So but then you kind of take your code and give it to someone else, give it to production, and you compile it. And when you compile it, you use a different version of malloc library, and that particular malloc library is handling things internally in a different fashion. So the particular thing which didn't cause a problem for you in when you're testing, it could give a problem for you when other production, when it is actually being deployed. Does it make sense?
Yeah, sir. I think I'm trying to get it.
So the reason, like understanding C is very nice because it gives it is very close to machine. Because of that, you see how things interact between machine and the high level programming language. And later on, when you, so the question like, why not use Python? So Python, no, understanding how, what happens at a higher level, mapping it to a lower level and understanding that interaction is a bit hard.
So, but then here, malloc isn't any different from new then, is it? Like new in C++.
Yeah, malloc is not different from new in C++, I guess. Yeah.
So it's the same.
Yeah, I think so. New also, whether it uses the same malloc library internally or no, it's just new is a syntactic sugar. I don't know. Uh, so we
So,
have
but
to,
once you
I
do
have to
new
check.
to a particular object, you can't cast it again, right?
Yeah, you can't. It's new car means
Uh,
it stays car.
oh, is it? Okay, that's C++, no? Object-oriented stuff. It will.
Yeah. So you can't like go into something like you can't cast any.
Yeah, that is a language level enforcement.
Oh,
But
but in
you can,
malloc you can cast it even after you store data like that.
Yeah,
yeah,
you can just keep
yeah,
changing
you
it
can
to
do whatever you
whatever
want.
you can do
Oh, then
anything.
malloc's much more versatile compared to
But you
new.
can malloc in C++ also. So
I didn't know. I don't know malloc. I don't know.
everything in
Beginner's
C you
level.
can just do in C++. So
Hmm. I mean, yeah, just include stdio and you can use everything there. So no, I'm not gonna try it anyway. So what's mmap? Like I didn't get the function.
Don't worry, you'll study later.
I
Not in
don't
the
know.
next
Like
year,
Kishore
third
told,
semester.
it adds a page to heap, which I
Yeah,
can't
that's
get.
what. So don't worry.
can I screen share temporarily?
Yeah, yeah, screen. If sir allows, I wanna
uh,
get this.
so I should stop the share so that you can share. I stopped it. You can please go
I
ahead.
think so. It's disabled for participants.
No, it's disabled. Sorry. Yeah, yeah, I should be able to.
Is this visible?
Oh yeah, it is. Oh god.
No, it's just the same thing, right? I just did this. With infinite loops, it just keeps allocating 1 million bytes.
Wait, can you show the code again? Malloc. Yeah, 1 million bytes to null. What? Why the equal to null?
Basically, if it fails, it'll return null, right?
Oh, okay. If not, it'll just keep allocating. Okay.
Yeah. So if we do this and run this with strace, all the okay, never mind. I'll take 1 0 off. But doing this, all of these are BRK, which is on the heap itself. But if you make this 1 million, then from here it'll start allocating on.
Okay, okay. It's allocating in a
On
different memory. But
yeah.
wait, you don't mmap just adds pages to heap, so it'll still be heap only, right? So it should still show BRK.
No, BRK means like in one page, it keeps moving how much memory you can access. Like in that page itself, you can just keep putting more. You can allocate more to yourself. mmap just puts a whole another page for you. Just go.
Another page doesn't. As far as I understand it, heap is like this amount of memory that you can dynamically allocate. So
Yeah,
how
but
do you add pages to it?
the heap's like a box, right? And then it's like so in the box you're only allowed to use like one part of it. So if you try to access a part of it that's not yours, it will crash or it will just segfault. So BRK just increases the amount you can access within the box, and mmap just puts another box for you.
But where does it get that memory from? From other
RAM.
parts of heap? Oh, from
No,
RAM.
from RAM just directly. It's cool. I think if
Okay. So
but
mmap is just like increasing your heap size.
yeah. So can you run this code, because on my PC this just crashes like really quickly. Like everything just gets it just gets stuck in like okay shit. On my computer this just crashes after like a few seconds. Then I can't run it after this. I don't know what happens once malloc gets freed. I don't see maps or anything, but it doesn't do anything either.
Wait, but then technically, even with this size, if like you're
Yeah,
using
okay.
malloc 10,000 after BRK is over, shouldn't it automatically access mmap?
Okay, now it crashed. Yeah, so I don't know why. Okay, it's still.
Maybe I am thinking if it is below some size, it tries to expand. If it is above some size, it tries to get a whole page or something.
So, but
Yes,
then if it's 10,000 and if it crosses BRK limit, shouldn't it access mmap then?
yeah. Oh wow, kill basic kill.
Why
So
won't it do
Okay,
that?
I think we should let me see. This is okay. I will. We just have to think a bit and do some research to understand what's going on. Um, we can hold a discussion for the time being
okay.
and see if there are any other. Rohan, how are you doing?
Hello.
Yeah, Rohan, how are you?
Yes, sir. Fine.
Tell me what's up, Rohan. So you're all doing good.
Yes, sir.
Any questions you have, Rohan?
No, sir, I joined to for the discussion which is going to learn.
Okay. Hmm. Good. Syed Isha. Isha, how are you?
Sorry, sir, I am Imami. It's
Oh,
my
Imami.
uh,
Okay.
I'm
So
using the account. Actually, I just joined to know. They said you are teaching pointers again, so I just wanted to revise it once. So I joined.
okay. You're doing all right?
Yes, sir. Or I think almost.
Okay. See, there's no rocket science, but you see, all of us forgot to use pen and pencil and try to work things out. So yeah, so just use pen, pencil, paper, and work it out, draw a picture. It becomes clear to you. All right,
Yes, sir. Thank you.
Aaron.
Hello, sir.
Yes, sir. How are
Yeah,
you?
my doubts were cleared. Other people asked
Cleared?
them. So
Good, good, very good.
thank you, sir.
Uh, Dhruv, how are you doing? Maybe Dhruv is not there. So, Varshita, what's up with you?
I haven't understood a lot in this class, sir, but it seemed really fun. I mean, I still have a lot of doubts about pointers, but yeah.
Okay, okay. So, Pramod, you were mentioning, some problem you have. So maybe we can take it up and then we can sign off.
Oh, the code, the
Yeah, the code, no,
troubles.
that so you said that why
Yeah.
I didn't get time to go through it carefully. So maybe if you didn't figure it out, we can think about it.
Yes. Kishore ran it on his machine, and for him, like it behaved kind of normally. Like the average case clocked in a slightly faster time than the worst case.
Mhm.
But for some reason on my PC, like every time it clocks in more time.
The average clocks in more time than worst case.
Worst
Huh?
case, yeah.
Mhm.
So should I show it to you?
Yeah, sure, sure. Yeah.
Okay. Is it visible?
Yeah.
So first I'll run the worst case maybe.
Mm. You have all cool prompt, man.
So so this I'm pretty sure it'll give a time around 24 seconds, I think.
Okay, 34 seconds. Huh?
24.
Okay. What is that echo doing?
So the first one is just putting that 10 power 5 into input
Oh,
output.
okay, okay.
And the
So
second
this
line
one
is,
is
it will print 10 power 5, 10 power 5 minus 1 all the way to
okay
1.
in the input.text file.
Yeah,
Okay,
it'll append it.
okay. So this is the worst case.
What? Oh, maybe my PC is slow right now, but yeah.
Okay, that's fine. Okay, so 35 seconds.
And then this program, it just generates,
Hmm.
up to one
Okay,
from 1 to 10 power 5 random order.
okay.
And this should be the average case.
Do you have perf installed on your machine?
uh, I don't think so. No, sir.
Let's see how the running time of this program, and then we can.
Yes, sir. Yeah, so it clocked in more time.
Can you do perf p or perf and
No, it's not installed.
install them? Can you do an apt install perf apt-get?
Oh,
Yeah. So what? How do we install perf? Can you just check?
I think it's a snap. I tried snap.
oh, is it?
Right, GPerf maybe?
What?
Oh yeah, or GPerf. One of those two. It was a snap or GPerf. One of those. Yeah.
Sure, if it's the exact thing.
But for me, it gave a prompt when I put sudo apt install perf. It gave something like the classic prompt.
It does. Is it
So can
should
you do perf stat minus d and run the dot? Or you should do sudo.
Oh,
It may be GPerf
E.
isn't.
One sec, I'll check mine.
Maybe just try snap install perf, I guess. Maybe it's
Okay,
not.
no, mine is perf. Mine is just perf, not gperf.
so is it sudo snap install?
I think so. Because I have perf installed, not gperf.
Oh, what?
Snap perf. It's not snap perf either. It's sudo apt install perf hyphen hyphen classic.
Or do search apt search perf.
Search what, sir?
I think if you just do Google, it will give
Oh,
the link. It's yours is Ubuntu, right?
yes, sir.
Yeah. Yeah. So you have to use just install sudo apt-get Linux tools.
Sudo apt install
Linux
Linux.
Linux dash tools.
Okay. I should select. Okay.
I sent it in Zoom chat also.
I can't. Where is the chat?
And there's a bunch of other stuff. I don't know.
Wait, but when I tried installing this stuff, it told broken something for me. Broken pipe or something.
I don't think. Oh, I should select one to install.
Wait, try the other one I sent.
So actually, Pramod,
Yeah.
I would like you to do this one thing actually. So before even we try this thing, can you print the swap count, the number every time a swap happens? Can you count the swap and
Okay.
print the number of swaps that happened in the worst case and the average case.
Yes, sir. Mm.
So you're all helping the new batch of students to settle down.
Yes. Very
You
good.
share your wisdom.
Some people they're still trying to install Linux, I think.
So time now is 7:36. So we will kind of conclude around 7:45. I'm hungry.
Sorry, sir. Oh, I should have used. Okay.
Use long.
Yeah.
Huh? Nice.
So that's the swaps
Good.
for
Yeah.
average case, I think.
That is for the average case, right?
I think.
170. Yeah, that's for average case. 173, 532.
Yeah, that's average.
Hey, we lost the time. Huh? The number of swaps, did we lose them?
No,
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 right?
it's
Okay.
okay. It's
Good. Okay. So in millions, it is 2,494 million or 2 billion swaps. Approximately 2.5 billion swaps
yeah, yeah.
for the average case.
Oh, this is yeah. Uh, 4, 5,
Yeah,
6,
this is
5.
4.9 billion.
Yeah. So 5. Yeah, 5 billion. But still, it clocks lesser time than.
It clocks lesser. Good question. Good question. Huh. Um, very interesting phenomenon.
There's nothing wrong with the code, right? Like this code.
In this particular case, I don't see any reason why it should give a problem.
And it's not just the like the recursive
Oh,
also.
this is recursive, huh?
Yeah, even the iterative is the same.
The same, huh?
Yeah, like it clocks more time.
It's interesting. I have to see, Pramod, because if you see the swaps are conforming to what we are expecting.
Yeah.
But so yeah, so what is happening? It's there is. I don't even usually this happens when there is problem with the. There could be one reason. There is one reason I can see. When we do the comparison, na,
Yes, sir.
so there is what is called as a branch prediction strategy in the processor. And in the worst case, all the time that the if statement turns out goes in one direction only.
Yeah.
And in order to understand that, the only way is to do perf and see what if you can you install perf, and I want you to see look at couple of things. One is called as a CPI, clocks instructions per clock cycle or clock cycles per instruction is one, and branch prediction ratio. There are a couple of things you will get. Can you kind
Yes.
of take a look at it and let me know what how those numbers are looking like?
Yes. Should I do it now or like are you getting late, sir?
Yeah, I guess so. Install first quickly. We will see. I will just join you back in 5 minutes,
Okay.
and then
Yeah.
meanwhile, hopefully, you can install it and
So,
yeah.
just one question: would inlining help with branch prediction? Would would that reduce effects if?
Would inlining help with branch prediction? Maybe not much actually.
Would it reduce the effects if it just saw that only the three same instructions, so it just
You
does it
can
anyway?
do this one, apt-get install Linux tools common, and that's
Yeah.
right. Yeah, what is that? No? Sudo. Yeah. What is that, Kishore? Inlining.
If we inline it and it sees it's the exact same three operations, can it just do it and then throw it away if it doesn't
Yeah,
need?
that's true. That's what most of the stuff in C++, no, get set functions, they will be inline.
So would that help branch prediction? Like, would it reduce the effects of branch
Not so much because, because all calls, they will be taken branches. So it's not, it's easy to predict.
No. So
Perf
perf.
stat minus D. Do
Is it?
minus D. Yeah. Perf stat minus D ls. Just do ls to see if it's working or not. Sudo.
Oh, sudo.
Yeah. So what we are looking for is instructions per cycle is one metric, and the branch misses 3.9%. Okay. So now can you do a perf stat minus D on the two versions? I'll just be back in a moment.
Yes, sir.
Okay.
Can you show the poster?
So anything interesting?
0% versus 8%, 9% branch misses.
Branch misses are 0.00, but you can see now the instructions per cycle.
So the
It is
next one is
2.44 instructions per cycle in the first case. The first case is what?
The worst case.
That's the worst case, huh?
Yes, sir.
Oh, okay. So in the worst case, more instructions per cycle are executed, huh?
Yeah.
Okay. In the second case, 1.40 instructions per cycle. And the branches misses are, there are more branch misses. And more importantly, if you see L1 cache loads, there are more in the first case,
but why?
but in the second case, the cache loads are less. I don't know why it is happening. LLC load misses 42.65%. This is load misses or less. Yeah, that I am not able to understand. I think my take is branches have a problem. It's causing some problem, and because of that, the branch prediction strategy is kind of working good in the worst case because it is always a taken branch and
So what
yeah,
exactly
that's
does branch prediction mean, sir?
so. Hmm.
So
So what?
sorry.
Yeah, someone go
No,
ahead. Krishna.
so you go ahead.
So what I think, so what happens is you have a sequence of instructions, and then there is a branch, and so maybe if you can permit me to annotate, I can.
Yes, sir. I'll stop. Should I stop share
No,
or
it's okay. I can keep it here. Maybe we will get. Just give me permission
allow
to annotate.
participants? Okay. Yes, sir.
Sir, and if it was branch prediction, why would worst case be slower on my machine?
Because the branch prediction on your machine is bad or
I mean, it is a 1700, so I mean it's fairly newish. So
I don't. Yeah, good points. I think I should also try it on my machine. So and see.
maybe VMs do something. Do they mess with branch prediction because it's on a
That
virtual?
is also possible. That's the thought I also got that VMs could be doing something. No, that.
So can
I'm
I?
still confused about what branch prediction actually does.
Yeah. So maybe you can just unshare. It seems I have.
There's like a 3-hour MIT course.
Okay. Now I think yeah. So
Or
here I
you
can. I
can
think I can
watch.
annotate now.
No.
Yes.
So usually what happens is you are able to see the screen, right?
Yes, sir.
So if we have some instruction like add R1, R2, R3, some, let's say some other multiply instruction, R4, R7, R9. So like that, some instructions, and then there is some other instruction add R2, R6, R4, R6. Let's say this is the destination. This is the destination. The first operand is the destination. So what happens is the processor, it launches this instruction. Let's call this as instruction I1. This is instruction I2. This is instruction I3. So if you see I1 and I2, they are independent of each other, but I3 is dependent on I2 because the value produced by I2 in register R4 is consumed by instruction I3. So when the processor, what the processor does is executes I1 and I2 in parallel. And then since I3 has a dependency on I2, I3 will be executed after I2. So this is what is called as an instruction level parallelism. ILP stands for instruction level parallelism.
So can you repeat that part?
So the processor aggressively goes and tries to find parallel instruction and tries to execute them. The problem is when it is trying to do it, let's say if there is some branch BEQ on L1, let's say L1 is something like this. When it hits a branch instruction, the problem for the processor is it cannot, it's a kind of a wall. It cannot go and aggressively find parallel instructions because the next instruction that will be executed depends upon the outcome of the condition that we check here. So yeah, so branch instructions reduce the amount of ILP that is available for the processor. But many branches are, so what processor does is in order to overcome it, it tries to predict the branches. That this branch will be with high probability, the condition will be true and it will be a taken branch. In the case of worst case execution of the bubble sort, the branch is always, the if condition is always true or false. Okay, so because of that, all the time swaps keep happening. So the processor, it's for all practical purposes, that's the if condition is like non-existent. It will just go ahead and execute the instructions in the if part of the. So that gives a lot of scope for the processor to go and find parallel instructions that can be executed in parallel. But on the contrary, if you have a, in the average case, if you have something like this, sometimes this will be true, sometimes this will be false. Because of that, all the branch prediction strategy which the processor uses goes haywire, and available instruction level parallelism to the processor will be limited. So due to that, if you see here, it will be 1.4 instructions per cycle, and this is 2.44 instructions per cycle.
So worst case is faster because the processor's like everything is anyway gonna swap. So why bother checking the condition?
Yeah, it is like kind of doing things in parallel. Yeah.
So, but how does the processor do that? Like the processor doesn't have a mind of its own, right? Like.
No, it has a mind of its own. Of course, you'll design that mind.
So is that software level, or is there any software behind it, or is it all at hardware level?
It's all at the hardware level. Compiler also kind of facilitates few things, but these are called as superscalar processors. Not all embedded systems processors, etc., they cannot do. Like for example, the processors in your mobile phone, they don't have this kind of capabilities. So, but on the processors on your mobile, on the desktop, they have.
So there is this thing where in your code you can ask the processor to try to prefetch stuff in cache free. So the compiler can sometimes just tell the CPU
that's true. Yeah.
So are if conditions does the predictability depend on just the probability of data you give it? Like if the data is like extremely skewed towards one condition, or do the conditions themselves matter? Like what kind of conditions?
No, if it is skewed towards one condition, it will be good.
So it only matters on the data you're given.
Yeah, that's true. So here, one thing I want you to observe, the number of instructions here are larger than the number of instructions here, but these instructions are executed much faster than these instructions. Makes sense, no? Can you see?
Makes sense, but
So let's say in the code, there is the if condition, right? I make an else if, and then say if swaps is let's say less than or no greater than or equal to some 4.5 billion, then break it.
Hmm.
So are you saying that that branch will never be accessed?
If
Because
swaps is greater than,
if swaps is greater than 4.5 billion, then
okay,
break the function, like exit the function.
okay,
So that would give us a wrong sorting, right? But
yeah.
are you saying that because the 4.5 billion swaps before that were like in the first branch, the first if branch, the processor won't even bother checking the other else?
I didn't get you exactly.
sir, I think what he's saying is if you put else if there, will it bother checking the else if? Because
Yeah.
it's already predicting everything, so it's not checking the condition at all. So if I put an else if after that, like else if break after 4.5 billion swaps, will it break after 4.5 billion swaps, or will it just ignore the condition and go ahead?
No, if it is break, it is break. No, I didn't understand that thing.
I think
But what? Okay.
I think what's happening is the processor predicts it and does the instruction itself, like it pre-does the instruction, and then it checks the condition. Like if the condition
Yeah,
is
that's
wrong
it's called a speculative execution.
and if it executes incorrectly, then it'll go back and it'll have to redo it. But it's like probability that it mostly predicts correctly.
Okay, so are you saying if it has to go back and redo it, where will it store that data that it just overwrote? Like it would be overwriting
In
some
order
data.
to, when the speculative prediction fails, you do a rollback, and will be very sophisticated mechanisms for rollback.
Okay.
Okay, guys, I'm really
So
hungry now.
Okay, sir.
so,
okay.
so
So
I,
one last
yeah,
doubt, sir.
sure.
So does the processor like the moral is the processor goes into the if branch, the first branch, without even checking the condition, does the instruction parallelly,
No,
and
no,
then
it checks the condition, but later it confirms it. It aggressively gets it,
so it
prefetches.
just so it does the condition before or checking the like
No, no, it
does the
executes the instructions in the if before, but
okay,
it gets confirmation later about that condition.
okay, sir.
Okay, and if the confirmation turns out to be wrong,
Then it goes.
this is not speculative prediction, it is speculative execution. Sorry.
Okay, now it makes more
So
sense.
just one thing. Any idea why the cache hits were more in the first? Like there were less misses in the first one.
Yeah, so that's what initially I was thinking, whether it will have an impact on cache misses. I am not sure why
Both times you're
would you.
going completely linearly through it, right? So why
Yeah.
would it? Oh, maybe because in the random one it has to swap things from like two different ends of the array, while in because in random it can. Do we? No wait.
No, not really,
Oh
because they
yeah,
are
yes.
just.
Yeah, yeah. Sorry.
Yeah, so that's the initial hunch, but I didn't feel it. But what I would say is, yeah, so there is when you install a load, um, what happens is when you issue a load instruction, in the case of the first, the load, so if the condition is there, so that there is some load, etc. are there. So what happens is, since you go ahead and invoke this load aggressively before, the latency between before invoking load and but the time lag between the invocation of load and invocation of load and availability of data, it will be sufficiently in advance so that the dependent instruction would not be in trouble. Or I don't know. I'm just rambling.
Oh, what?
Yeah, so not sure. So, but if you see, not like the misses wise, I don't think there is any difference. LLC misses, it is 36%, 42%, and what is different is this one. L1 D cache loads
Yeah.
and this one. I think this will have a huge impact on the performance. And I would maybe I want you to check, see what this L1 D cache load and try to understand. Okay.
Okay.
Yes, sir.
All right then. Awesome. So
Yes.
Thank you so much,
Thank you,
sir.
sir.
yeah,
Thank you, sir.
it's fun. Yeah. So we'll conclude. Okay.
Yes, sir.
Have a
Thank
great weekend.
Yes,
Bye.
sir.
Thank you, sir.
Bye, sir.
Bye.
Sure, sir.